Squeeze anything hard enough and it turns into a black hole. Doesn't matter if it's a rock, a glass of water, an onion, or one of those tiny dogs that never stops barking. Compress all that mass into a small enough space, and gravity becomes so overwhelming that not even light can escape it. But what exactly counts as small enough? Every mass has its own critical size. Squeeze an object past that threshold, and it stops being an object and becomes a black hole. That threshold is called the Schwarzschild radius. Cross it, and an invisible boundary appears, the event horizon. Light outside it can still get away. Light inside it is trapped forever. Here's the fun part. The Schwarzschild radius can be calculated for literally anything. Take an average professional athlete weighing 75 kilograms. Compress his entire mass down to that critical radius, and you'd get a black hole roughly 10 to the negative 25th power of a meter across. For comparison, a proton measures around 10 to the negative 15th power of a meter. In other words, you'd have to compress a human body down to a volume 10 billion times smaller than a proton. Under the laws of physics as we know them, that's flatly impossible. But mathematically, the math checks out perfectly. Let's go bigger, say the entire Mediterranean Sea. Compress all that water down to its Schwarzschild radius, and the resulting black hole would measure about 6 nanometers across, roughly the size of a large protein molecule. Now, what if we compressed the whole Earth? Its Schwarzschild radius comes out to about 9 millimeters. That means our entire planet would shrink down to the size of a marble, a rare case where a cosmic scale number actually fits inside a human brain. Tiny black holes, though, don't stick around for long. Over time, they lose mass through a process called Hawking radiation, and the smaller the black hole, the faster it evaporates. A black hole made from our 75-kilogram athlete would exist for a grand total of 35 trillionths of a second. A 40-ton truck would evaporate in about 5 milliseconds. A Boeing 747 would vanish in 7 seconds. The Eiffel Tower would hold on for about a day. The Titanic, 140 days. And a large aircraft carrier, 2.7 years. And once a black hole finishes evaporating completely, its entire mass gets released as a staggering burst of energy. But how much energy exactly? For reference, the bomb dropped on Hiroshima released about 15 kilotons of TNT equivalent. The most powerful nuclear weapon ever detonated, the Tsar Bomba, released around 50 megatons. With that as our yardstick, the energy released by our human mass black hole evaporating would be roughly equal to 32 Tsar Bombas. A loaded truck? 17,000 Tsar Bombas. A Boeing 747? 190,000. The Eiffel Tower? 4.3 million. The Titanic? 22 million. And an aircraft carrier? 43 million. Tsar Bombas. An explosion on that scale would do irreversible damage to the planet. Now picture this. We've compressed the entire Earth into a black hole the size of a marble. What happens to the Moon? Disappointingly, nothing much. The Moon just keeps right on orbiting, completely unbothered, except now it's circling a black hole instead of a planet. As long as the mass is still there, the Moon doesn't care what's holding it in place. It was never in love with the planet, just its gravity. Says a lot about you, Moon. Anyway, let's keep going. Let's crush the most massive planet in the solar system, Jupiter, which weighs more than every other planet combined. After compression, the resulting black hole's radius comes out to about 3 meters, roughly the size of a large delivery van. We're finally starting to see some real volume here, but we need something truly colossal. Compress the sun, and you'd need a map instead of a ruler. The radius of that black hole would be about 3 kilometers, comparable in size to an entire city like Barcelona. The sun's entire mass, contained within the footprint of a single metropolis. And here's the interesting part. A black hole doesn't have to stay that size forever. Once it forms, it can keep growing by consuming everything around it: gas, dust, entire clouds of matter. In some cases, it can swallow whole stars, entire planetary systems, or merge with another black hole, growing rapidly in both size and power. But here's the catch. We haven't actually found a black hole the size of a compressed sun. So what's the smallest one we do know about? There's no clear winner, just a handful of candidates, but everything points to a minimum of 3 solar masses being required to form a black hole at all. To get a sense of just how small that really is, an object like that would have a radius of about 9 kilometers, somewhere between the height of Mount Everest, 8.8 kilometers, and the height of Olympus Mons on Mars, the tallest mountain in the entire solar system, at around 22 kilometers. That's the theoretical floor for black hole size, remarkably modest given the cosmic terror we usually associate with these things. Which black hole is closest to Earth? That honor belongs to an object called Gaia BH1, sitting 1,560 light-years away. With a mass of 9.6 suns and a radius of about 28 kilometers, it's more compact than the footprint of Greater Tokyo. In other words, the black hole closest to us is still completely unreachable, and even so, it's no bigger than a large city. But enough about modest scales. Everything so far has been a stellar mass black hole, the kind born when a massive star dies and its core collapses. We're here for scale, for something genuinely unimaginable. Let's start with intermediate mass black holes, which usually don't form from a single star, but inside incredibly dense star clusters, where the heaviest objects sink toward the center and trigger a chain reaction of mergers. A solid example is an object called HLX-1. By the most common estimates, its mass comes in at around 20,000 suns, with a radius of about 59,000 kilometers, practically the size of Jupiter. Some estimates push its mass as high as 100,000 solar masses, in which case the event horizon's radius would grow to around 300,000 kilometers. Set a black hole like that next to the sun, and it would come out at almost half the sun's size. But if you want the real jump in scale, welcome to supermassive black holes, the monsters that live at the centers of galaxies. What's sitting at the heart of our own Milky Way? Meet Sagittarius A star, with a mass of 4.3 million suns. Translated into the size of its event horizon, that's about 12.7 million kilometers. And here's a curious detail. By astronomical standards, that's actually not all that much. To put it in perspective, if we removed the sun and dropped this black hole in its place, Mercury's orbit wouldn't even come close to touching it. The monster running our entire galaxy fits comfortably, with plenty of room to spare, inside the orbit of the smallest planet in our solar system. But our own central black hole clearly isn't the biggest thing in the universe. Step it up one more level and you meet M87 star, the subject of humanity's first ever photograph of a black hole, sitting at the center of a colossal galaxy. Its mass comes in at around 6.5 billion suns, with a radius of about 19 billion kilometers. Drop M87 into the center of our own planetary system, and it wouldn't just swallow Mercury. It would take every single planet, Pluto included, whose orbit sits about 6 billion kilometers out. M87's edge reaches 19 billion kilometers, meaning this black hole is 3 times bigger than our entire classical planetary system. There would be exactly one survivor, Voyager 1. Launched in 1977, it's the most distant human-made object in history, and right now, in late 2026, it sits roughly 25.5 billion kilometers from Earth. This November, in fact, it's set to become the first thing humanity has ever built to reach a full light day away from us. If M87 showed up in the sun's place right this moment, Voyager would be the sole surviving witness that we ever existed at all. So we need something that swallows absolutely everything. A genuine final boss. Tone-618 held that title for a long time. The original estimates put its mass at a staggering 66 billion suns. More precise measurements of the gas orbiting it, though, forced astronomers to revise that number down to somewhere around 40 billion solar masses. At that mass, the object's radius comes out to about 118 billion kilometers, enough to fit more than 6 M87s inside it. For comparison, light takes about 11 hours to cross the entire solar system from end to end. Crossing Tone-618, that same beam of light would need more than 9 full days, traveling at 300,000 kilometers per second. And yet, even Tone-618 probably isn't the biggest black hole in the universe, just the biggest one we've managed to reliably measure so far. In the summer of 2025, astronomers announced something even more massive, a black hole found at the center of the cosmic horseshoe gravitational lens. Its mass, measured using an especially reliable method, coming in at around 36 billion suns. And according to physicists' calculations, a black hole growing continuously since the birth of the universe could, in theory, reach a maximum of around 50 billion solar masses over the universe's current age of 13.8 billion years, which appears to be the practical ceiling for objects like this. Every time we improve our telescopes, every time we look a little farther, the universe finds a new way to surprise us, and to remind us just how small we really are. It's a reminder that we live in a universe that isn't just bigger than we imagine, it's bigger than we're even capable of imagining.